Welcome back to Honors Calculus. In this video, we're going to be talking about optimization problems. Optimization is the natural application of absolute and relative extrema and of the extreme value theorem. The idea of optimization is looking at a scenario and trying to find the most efficient way of doing something. For example, using the smallest amount of material to make a box that will hold a particular volume of content, or tying a rope to two posts using the minimum amount of rope. The approach that we're going to use for solving optimization problems, very simply, is to take the situation, try to write a function representing the thing that we care about, and then finding the extreme values of that function, assuming that our solution is going to be somewhere in that mix. So without further ado, let me get my head out of the way and let's dive into one. We're going to look at a relatively straightforward papercraft project. So I want you to visualize a sheet of paper. And from that sheet of paper, I am going to cut out a square from each of the four corners. And by doing that, this square will turn into, or this piece of paper will turn into a shape that has four flaps. I can then fold each of those flaps and tape them together, creating a box with an opening on the top. So it is a rectangular prism, but it does not have a top surface. Let's say that this is a standard sheet of US letter paper. So that dimension is 11.5 inches. I'm sorry. I said standard US paper, not European paper. That side is 11 inches. This side is 8.5 inches. All right, we're going to cut some amount of material out of each of these corners. And again, each of these corners is going to be perfectly square so that when the sides get folded up, the edges match together. Right? This edge must be the exact same length as that edge so that when you fold them together, they meet and they line up nicely. This edge must be the same as that edge so that this piece is a rectangle and it folds up straight. This and this must be the same, this and this must be the same, this and this must be the same. Going around, you find out that all of these edges have to be the exact same length in order for this to work. Let's call that length x. And our task is to find the value of x, which will maximize the volume of the box. Before I get into trying to set anything up, in order to make sure that I understand the situation, one of the things that I like to do is think about what is the range of plausible values for x. Clearly, the minimum value of x is 0. If you cut nothing out, you get a flat sheet of paper. That's boring. We need to have x bigger than 0. The maximum value of x takes a little bit of thinking. The biggest value of x that you can choose is going to be a value where the square you cut from the top and the square you cut from the bottom are in fact the same square, so you're just cutting everything down. And you're left with, once again, a flat sheet that doesn't have anything buckling up. And since the shorter length is 8.5, the maximum cut that you can take is half of that. So 8.5 over 2, which is 4.25. All right, so we know that x is somewhere between 0 and 4.25. That gives us something to work with. Now, the next thing we need to do is try to think about this box. After we cut these edges out and we fold this shape, we are going to end up with something that has in fact been folded into a nice box. It's going to be a box that has no top in it, but we can try to work through and figure out what the dimensions of this box are going to be. It's actually not that challenging to do. The height of the box is going to be x. That's the height of the wall here. The width of the box is going to be whatever is left in here. And we know that the total distance across is 11. We've cut out this bit that is x, and we've cut out this bit that is also x. So the length here is going to be 11 minus 2x. And then we can do the same thing with the width. The width is the bit that's inside here. The total distance is 8.5. We cut out x, we cut out x. The part that's left is 8.5 minus 2x. And that gives us a formula for the volume of the box. Right, it's going to be a little bit of a pain to multiply this out, but we know that we're going to be taking a derivative, and multiplying it out before we take a derivative is very useful. All right, so 11 times 8.5 is 93.5. 11 times 2 is 22. 2 times 8.5 is 17. Multiply that, or add those things together, we get that this is going to be minus 39x. Then we have minus 2x times minus 2x, which is going to be plus 4x squared. And then multiply all of that times x, and we get 93.5x minus 39x squared plus 4x cubed. All right, so this gives us a formula for the volume of the box, given the size of the cutout that we take. This is a cubic polynomial. We can figure out where the roots are if we so desire, but the thing that's really going to matter, again, is we want to find the maximum value of v. And the maximum value of v must occur at one of the endpoints, x is 0 or x is 4.25, although we know that those are both going to give us a volume of 0, so those are hopefully the minimum values, or it will occur at a critical value, a place where v prime is equal to 0. So differentiating here, derivative of 93.5x is 93.5. The derivative of 39x squared is going to be 78x. The derivative of 4x cubed is going to be 12x squared. And because I've got a decimal number floating about in here, I'm not even going to bother trying to factor. I'm going to jump straight into the quadratic formula. X is the opposite of negative 78, which is 78, plus or minus the square root of 78 squared minus 4 times 12 times 93.5 all over 2 times a, which is 12. My calculator is happy to do some of the work for us, although because it involves square roots, I do try to do things in multiple steps instead of everything all at once. 78 squared is 6,084. 4 times 12 times 93.5 is 4,488. And 2 times 12 is 24. 6,084 minus 4,488 is 1,596. And square root of 1,596. That's not one that I know offhand. Although this is actually a pretty easy one to figure out. 1,596 is incredibly close to 1,600. And the square root of 1,600 is the square root of 16 times the square root of 100. 4 times 10 or 40. So this is going to be really close to 40. In fact, if you grab your calculator, it's going to come out as 39.95. All right, so we've got 73 plus 39.95, all divided by 24. Which comes out around 4.71. And we've got 73 minus 39.95, all divided by 24, which comes out at about 1.38. If you go back to where we started on this whole process, we said that the value of x was going to be somewhere between 0 and 4.25, which means it's definitely not going to be 4.71. It is going to be this value, 1.38. So I would like you to look at a problem that's going to look very different at first glance, but somewhat related. we've got two poles of different height that are set up on the ground. The distance between the two poles is 30 feet. One of the poles is 10 feet tall. The other pole is 20 feet tall. We are going to connect a guy wire to the top of one pole to an anchor on the ground and then continue on to the top of the other pole as a piece to help us support these poles and make sure that they stay the same height. Your task is to figure out where to put this pole to minimize the length of the guy wire. Something to get you started along the way. I think that you will notice that the anchor has to be somewhere on the straight line between the two poles. If the anchor is anywhere else in three-dimensional space, right? Imagine that this is the straight line between the two poles. If I put the anchor over here, now I have to go out and back, which is using a lot more wire than if I just went straight down. So we know that this is a problem in just one dimension. That's something very important. Another thing that I'm going to give you, let's call the length from the pole to the anchor L1. And then from the anchor to the top of the other pole is going to be L2. And the thing that we are trying to minimize is the total length, which is L1 plus L2. All right, get my head out of the way so you can actually see where I've written that down. All right, but there's a couple of hints to try to get you started along the way. We know a couple of lengths. We have a specific unknown given here. We can try to figure out a couple of other things. I would like you to take a few minutes and see what you can come up with on this problem. All right. And then once you have something, I'll see you here for the next video.